Welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk, but if you have questions, you can unmute and ask questions, or use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed, so please watch out. And finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now, let me briefly introduce our speaker today. It is an honor to host Elizabeth Quian, who is an assistant professor at Georgia Tech, jointly appointed in the School of Aerospace Engineering and the School of Computational Science and Engineering. Her interdisciplinary research develops new computational methods to enable engineering design and decision-making for complex systems with special expertise in model reduction, scientific machine learning, and multi-fidelity methods. Recent awards include a 2024 Air Force Young Investigator Award and a 2023 Hans Fischer Visiting Fellowship at the Technical University of Munich. Prior to joining Georgia Tech, she was a von Karman instructor at Caltech in the Department of Computing and Mathematical Sciences. She earned her SB, SM, and PhD degrees from MIT. Today, Elizabeth will talk about multi-fidelity linear regression for scientific machine learning from scarce data. I'm sure she's going to give a wonderful talk, so please have a high expectation. But before I pass the baton to Elizabeth, let me ask one question. I happen to know that the one sport you regularly do, like once a week, is the rock climbing. I'm sure a lot of people are already familiar with rock climbing among the audiences, but some are not. So if you can briefly introduce why you are so into the rock climbing and, advertise rock climbing to them.
Oh, goodness. Okay, well, if you haven't tried rock climbing, it is an Olympic sport, and the men's and women's Olympic events are going to be next week, I think. So you should look up the schedule and watch because it's pretty cool to watch. And that will also be my pitch for why you should do it because I think it's a nice sport for watching because when you go to the gym, you can try to climb, and then when you are tired and don't feel like actively climbing yourself, it can be pretty fun to watch other people like try to do the climbs. So I think it's a nice pastime.
Nice. You can utilize your time in maximum enjoyment.
Yes.
Awesome. Okay. Well, floor is yours, Elizabeth.
All right. So yeah, thank you for the invitation, Youngsu, to speak in this seminar. And I'm very pleased today to present some recent work that has been submitted, came back from review, and we've resubmitted the revisions. So fingers crossed that it will be accepted for publication. And so this is joint work with Anirban Chaudhary, who is a research scientist at UT Austin, and with my student Dayang Kang at Georgia Tech and his student Vignesh Sella at UT Austin. So before I start, I want to say that I typically like to take questions throughout the talk, so I will try to pause in a couple places to see if there are questions, and I'll also ask Youngsu to help me monitor the chat and just interrupt if there's like a clarifying question. I just think talks work better if I can address things along the way rather than saving everything to the end, and I've planned the talk so that there should be time for that. All right, so the motivation for this work, as well as most of my work, is to support decision making in engineering and science. And when we think about the decisions that we might want to make, a lot of times they rely on what I will call a many query computation. So that includes things like optimization, uncertainty quantification, and control tasks. So in optimization, you might have to query a model at every step of a gradient-based iterative method. In uncertainty quantification, you would be querying a model for every sample of, say, like a Monte Carlo, like uncertainty quantification computation. And in control computations, you're querying the model basically, at every second, say, in real time to understand like what the next control input should be. So traditional numerical simulations that comprise most of our traditional models are based on physics. They're often high dimensional because they result from discretizing a continuous governing equation on a high dimensional computational mesh, and that makes them generally too expensive for this many query setting. So these, you're not going to be solving these traditional high dimensional simulations, in real time, say for control, or you can't afford to do that many samples in uncertainty quantification. So there's a real need for efficient, and when I say efficient, I'm thinking like fast, so computationally efficient and cheap surrogate models to enable decision making. So I think everybody would probably agree that there's been a lot of interest in machine learning methods for surrogate modeling for engineering systems. They've shown a lot of promise. Partially through some very visible successes in other domains that were traditionally seen as extremely challenging. So in computer vision and natural language processing and in say playing the game of Go. So they've seen some real practical successes. And in addition to those practical successes, there are some theoretical guarantees of what I call the expressive power of these machine learning models. So I'm thinking in particular about neural networks, for which there are a lot of theoretical guarantees that say like there is a neural network of some shape and size and form with some parameters that can match like, sort of any complex nonlinear function, like perfectly, essentially. But there's a significant gap between that theory and engineering practice. And that's because of like basically what I was saying, like there is a neural network that can match things perfectly. It's just we don't know a lot about like what the neural network is, like what its architecture is, what its parameters should be. And so because there's that gap between the theory and the practice, there's a real lack of trust, I think, for using these machine learned models for engineering design where you have some consequences that impact that have like high costs both in terms of dollars but also in terms of like potentially human safety. And so that's a significant barrier to the widespread adoption of machine learning type methods in engineering. So to address that, one might ask, what is the reason that we have trust in traditional numerical simulations? And I would say that some of the reasons for trust in traditional numerical simulations are that they're based in physics, which is something that we sort of understand to be true, so there's a strong foundation. Additionally, we make some really explicit and transparent modeling assumptions in physics-based simulations. So for example, like if you're going to simulate a fluid flow with Euler versus Navier-Stokes, like you know that you're making an assumption in Euler equations that like the viscous effects are negligible. And that helps you understand, both when to trust the simulations as well as when we don't. And in addition, we have, many decades of numerical analysis that help us understand the errors in these discretized, these like sort of discretized PDE models. So then we ask, okay, so in machine learning or in statistical learning, like where do we get trust from? And I would, in sort of many of these applications, trust comes from big data, like the idea that you have so much data that like you've kind of like seen everything there is to see and you can really represent like that reality quite accurately. Okay, so to be more mathematically specific about what that trust means, I'm going to say, okay, we're going to consider an input random variable z and an output random variable y1. And y1 is some function f1 of z. And in the setting that I'm considering, I really think of F1 as being an expensive computational model, although you could think of it as also perhaps being a physical experiment. But like, let's just think of it as a expensive computational model. So maybe this is something you'd run on a supercomputer to get like the output Y of Z. And so the surrogate modeling problem from data is then to say, okay, let's suppose that F hat is a parameterized model with parameters beta. And so I can choose some parameters beta, and then I have some input, and then I can give it my input variable z, and it will predict outputs. So the machine learning task is then to find the best parameters of that model. So I want to find the beta star that minimize, this is a standard loss. So this is, in this case, we're minimizing the square of the error of the surrogate model. And notice like we have an expectation here. So that's sort of like over the joint distribution of the input and output data. And because often we cannot easily compute these expectations exactly, the standard thing then is to approximate this from data. So now I suppose I have input and output pairs. So like I have capital N of them, and so then I've got Zi as being the inputs and then Yi as being the outputs. And so then I, instead of minimizing the exact expectations, we'll try to find the beta that minimize the empirical mean square error. So this setup, I think, is has become quite widespread and maybe familiar. All right, so this is the problem that is being solved in machine learning generally. And essentially, when I say trust comes from big data, mathematically we're saying if that n is large enough, then this empirical mean square error minimization well approximates this true mean square error minimization. And so if n is large enough, then we trust that the training performance is going to be representative of what we call the test performance. So, you know, how we would do on data that's not on inputs that are not in this training set. But in engineering settings, n is often small because each of these yi1 data points comes from evaluating that expensive model. And so we're often pretty far from the setting in which we might say, like, one could implicitly trust that minimizing this error is representative of minimizing that error overall. And so the main idea of today's talk is to address that lack of trust due to small n or scarce data by combining our limited expensive high fidelity data with some greater volumes of cheaper low fidelity data. In order to address the small data challenge. And when I say small data, I'm really talking about that small high fidelity data. And so what I'm going to present today is a new method for multi-fidelity linear regression. So acknowledging that linear regression models are not as general as the neural networks that I was motivating the talk with, but seeing this as kind of a step towards more general machine learning models. And in that linear regression setting, we're going to develop a new method that's based on multi-fidelity control variates. I'll explain what those are. I'll present some bias and variance analysis that help us understand the accuracy and robustness of the models that we learn from the multi-fidelity data. And then I have some numerical results that demonstrate the sort of potential for this multi-fidelity method to really address these small data training challenges. So I will pause right here and just see if there were any questions so far about like the notation, the setup, or anything else.
I don't see questions in chat yet.
Yeah. Yeah, it's a pedagogical technique I've learned to give a long pause in case people formulate questions.
Oh, nice.
Yeah. Okay, well then I will jump right into the first part of the talk. Okay, so I'm going to talk about multi-fidelity control variate methods. Okay. So control variates are a technique or a family of methods that actually arise from Monte Carlo estimation of statistics, and the goal is to reduce the variance of Monte Carlo estimators. So I'm going to set aside the machine learning problem for now and just think about like a standard Monte Carlo estimate of like the output mean. So if I wanted to estimate the mean of f1 of my random variable z, and I had n samples of the input zi, then I could have standard Monte Carlo estimator, which is just the sample mean of the outputs. And we know that this estimator is unbiased, so that the expectation of this estimator is the expectation of the true mean, and that the variance scales with 1 over n. Okay? And so if n is large, then this variance is quite small, and so we think that the estimator, we would say the estimator has a low standard error, and then if n is very small, then this variance could be quite large, and so this estimator could have quite a high standard error. So the goal of control variates is to reduce the variance of the estimator. And the way we do that is we introduce like another random variable. So like, I'll tell you what it is in a second, but like suppose that we have another random variable w and it's correlated with the outputs. So it's, maybe think of it as an approximation. So it's well correlated with the outputs, and suppose for now that we know what the mean of that random variable is. So we like have some exact expression for the mean of w. then this formula defines the control variate estimator. So we've got mu hat, and I use CV to say this is the control variate estimator. And so we have this first term, which is kind of the standard original estimator. And then we add a second term, which is a correction. And that correction is basically the true mean minus the sample mean of the W's, okay? And so the key here is that these WI's are correlated with these F1 of ZI's. Okay, so this estimator has some nice properties. The first one is that this control variate estimator does not introduce bias. And that's because in expectation, like the expectation of W is mu W, right? So that term just goes away in expectation. So that's nice. And alpha, I should say, is some kind of scaling coefficient. I'll talk about it more later, but just think of it as a constant for now. The second property, I guess, that we want to analyze is the variance of this control variate estimator, which is related to the standard error of the estimator. And so I can give an expression for the variance of the estimator just by expanding the sort of covariance definition of variance. And this is what I get in terms of alpha. So you see there's, kind of here's the variance of the first term, like here's the variance of the second term, and then here's kind of the sort of cross term. And you can minimize this expression with respect to alpha and find an alpha star, which minimizes the overall variance of this estimator. And that alpha star is given by this expression. So it's the covariance of the model with your W divided by the variance of W. So if I now stick that alpha star into this expression, this is what I get. Okay, so with the optimal alpha star, you'll see that the variance of the control variate estimator is the variance of the original Monte Carlo estimator minus something positive or not negative. And so essentially the takeaway is that the higher the correlation between F1 and W, the greater the variance reduction. And that makes, I think, some intuitive sense.
Elizabeth?
Yeah.
There's just some questions. Do you want to take it?
Mm-hmm.
All right. The first question is from Kevin. Do we need to know the exact mean and the same number of samples are used for W?
Yeah, so we will end up estimating the mean of W. In fact, I just introduced it with the exact mean just to get the idea across. And I will talk a little bit more about the number of samples of W. But yeah, I'm introducing it with the same number of samples here because it's just a bit simpler to not have to have a lot of different letters running around, but we can relax that. It can be kind of, there are different sampling strategies.
All right, sure. And the second question from Dushyant is asking, are you ignoring the intercept term in the linear regression? General form is y is equal to mx plus c. I see you use the y is equal to mx function.
In my numerical experiments, I do indeed have an intercept. So we allow kind of a constant, like, one of the columns of the linear regression matrix is a bunch of ones. Although I don't remember having that on a slide yet.
All right. Okay.
Yeah.
That's it.
Thank you for the questions. All right, so yeah, so this is the main idea of control variates. Basically, the higher the correlation between W and F1 of Z, the greater your variance reduction. And so multi-fidelity control variant methods are based on this idea where we use lower fidelity models to define that W. And so now I'm going to say, suppose I have some function f2. So think of this as maybe a coarser grid than f1, or maybe, some simplifying assumptions are made relative to f1 so that this runs faster. Then this is the way I define the approximate control variate. And so to Kevin's question, like notice here now I have replaced the exact mean with a sample mean. And what I'm showing you is really the sampling strategy that's based on what some people would say is the multi-fidelity Monte Carlo method. And then there's kind of variants of this where you can have, different numbers of samples for each of these things. But basically I'm saying that F2 is cheap, so I can afford many more samples of F2 than I can of F1. So this is kind of a high sample approximation of the mean of F2. So this, instead of knowing the mean of W exactly, I'm approximating it with a lot of samples. And I can easily generalize this to many other low fidelity models just by adding, additional terms. So for like the F3 term, you would have something like this. For the F4 term, you'd have something like this. And there are several variations on this theme. So what I'm using in this talk is from this multi-fidelity Monte Carlo paper, which is a 2016 paper by Benjamin Peyerstorfer and collaborators. But Alex Gorodetsky at Michigan has done a lot of work to generalize that. And so that would be, this work would really kind of allow N and M here to really vary in more general ways. And another variant is known as ML-BLUE, or multi-level best linear unbiased estimators, by Daniel Schad and Elizabeth Ullmann. And that would allow sort of even more general structures, like you would have sort of different model groupings, just to give you a flavor of what exists. But these latter two are a little bit more complicated, I think, just in terms of the notation in particular. So I'm sticking with multi-fidelity Monte Carlo just to introduce the main idea. Okay. So, I've introduced the main control variate idea, and now I'm saying, okay, I'm using low fidelity models to define the control variates. And so those low fidelity models are being used to generate correlated samples that are going to help me reduce the variance of my Monte Carlo estimator. That's kind of the punchline. Are there questions? All right. So, yeah, this is just kind of highlighting again what I was saying. So this is n expensive samples, and n is not very large from the high fidelity model. And now I have lots of cheaper samples from the low fidelity model that are used to compute this correction. In this 2016 paper, Benjamin Peyerstorfer shows that like the multi-fidelity Monte Carlo estimator has lower variance than the Monte Carlo estimator of equivalent cost. So like there's kind of a constraint there saying like, okay, I'm trading off some of my high fidelity samples to get low fidelity samples under certain technical conditions, which I will summarize here by saying if the high and low fidelity models are sufficiently well correlated and if the ratio of costs between models is sufficiently high. And the detailed conditions are in that 2016 paper. Additionally, in that paper, they look at the influence of what you might think of as hyperparameters of the method. So like, what's the best alpha? What are the best M and N in this sampling structure? And essentially, you can formulate an optimization problem to say, like, what is the alpha N and M that minimize the variance of the MFMC estimator? And there's an analytical solution to that problem, and the analytical solution then depends on second order statistics of the models. So sigma being the standard deviation of F1 and F2, and rho being the Pearson correlation coefficient, so the second order correlation coefficient. Because in many settings, those statistics are not exactly known, the standard practice then is to use a small number of pilot samples to estimate those statistics, and then you get an estimate of the optimal alpha N and M that you would then use to figure out the number of the N, M, and alpha to implement this estimator. Okay. I see a question. Do I understand correctly? One needs M plus M samples of F2. In multi-fidelity Monte Carlo, actually, these are nested samples. So it's M total, and then these N are the first N of those M. But in some of the general variants that I mentioned, things are a little bit different. But yeah, you need a lot more samples of F2 than of F1 in general. All right, so that's the sort of background on multi-fidelity Monte Carlo. And so what I want to explain now is how we use this for multi-fidelity linear regression. Okay, so back to our linear regression problem. I have the input random variable z, output random variable y1, and where y1 is related to z through this high fidelity model, which is expensive. So now I restrict to this linear regression setting. So I'm going to say let x denote features of the input. Okay, and so this is where like I could have a constant feature to allow an intercept, right? And so x could be like polynomial features, they could be Fourier features, they could be features chosen from some physics-informed library, but whatever they are, I'm going to have a linear combination of those features determine my output. So this is my model class. So beta are my linear regression coefficients. And so now just going back one. Okay, so this is my linear regression task, basically minimize this expected error. All right, so this linear regression problem is very well understood. So its solution is given by this formula. So just the expectation of XX transpose inverse times the expectation of X times Y. So just note this is a square matrix and this is a vector. Okay, so I'm gonna just note those expectations by CXX and CXY because like this is a covariance matrix and this is in a sense like the covariance of the inputs with the output. And just remind folks that if X and Y are centered, so if they have mean 0, then these are these covariances, and then the optimal beta star satisfies this interpretation of the residual of the model being orthogonal to the features. So the standard way we approximate this solution, because this obviously has exact expectations, is to say, okay, now given data pairs, n data pairs of inputs and outputs, I will then approximate these covariance matrices with the sample. So these are sample covariances. And then my beta hat or beta tilde n, I forget what I used. Oops, sorry. Okay, then my approximation is just given by like inverting this sample covariance, multiplying it by this other sample covariance. Okay, so that's standard, but I'm actually not going to use the standard approximation. And the main reason for that is that this is actually not an unbiased estimator of beta star. And that's because CXXN here is unbiased for estimating CXX, but then once you invert it, like the inverse of the unbiased estimator is not an unbiased estimator for the inverse. And for reasons that will become clear, I care very much about it being unbiased. So I'm going to do a modified approximation of a linear regression solution, where instead I'm just going to assume that I have CXX exactly. Okay? The justification for that is to say, well, the expensive part of getting data is really getting Y1, right? Like every output requires that I evaluate this expensive model, but in theory, I could get lots of inputs for free and basically have so many input samples that I could assume that I have a very good or exact estimator of CXX, because that only depends on the features and not on the output of the model. And the other main reason, like I said, is because this is now unbiased. This beta has is unbiased estimator for beta star, and that's going to be important for us in our multi-fidelity model. Any questions about this setup? Giselle asked if F1 and F2 have to share an input domain. Yes, like so far we've just kind of assumed that they have the same inputs. If they don't have the same inputs, you'll need to do more research. Yeah. But that is an interesting case that, of course, we're aware of and thinking about how to handle. Yep. Okay, so that's the high fidelity linear regression setup. And so having chosen the parameters using that n high fidelity data estimator, we define a trained model using those parameters. And now if I think about for a given input z, like what is the variance of the model predictions? So f hat, like the variance depending on what the data are, then in fact that variance can be related to the covariance of these beta hat n's. So of those parameter estimates, which is what this says. So the variance in model predictions comes from variance in the parameter estimates, and the variance in parameter estimates comes from variance in these like CXY estimates. And so if we have a small n, we would have high variance in these CXY estimates, and therefore high variance in these beta n estimates, and therefore high variance in the learned model predictions. And so that really kind of kills your robustness, like thinking like training on this small data set versus that small data set might lead to very high, like changes in the model predictions. So the main idea of multi-fidelity linear regression in this paper is that we're going to use multi-fidelity control variates to reduce the variance of this CXY estimate, which is then going to lower the variance of the betas, which is going to lower the variance of the predictions, which is going to improve the learned model robustness. Okay, so that's what's on this slide. Basically, I'm saying I'm defining a multi-fidelity estimator of CXY using this multi-fidelity Monte Carlo form. So it's similar form to what's before. I mean, those sums have gone away because the sums are kind of being written as these matrix vector products, but you have this like M sample estimate minus this N sample estimate. So you should recognize that form. Something that is different is that this is a d-dimensional vector that is being estimated. So whereas alpha was a scalar coefficient before here, I've now replaced that with an A, which is a matrix coefficient. So you can think of it as kind of like a gain. Okay, just said that. And so with this estimator, this multi-fidelity estimator of CXY, then I have a multi-fidelity estimator of beta, which gives me a multi-fidelity learned model that uses those parameter estimates. So this is kind of the main idea of the whole paper. All right. So what I want to talk about next is some of the analysis we're able to do with this approach. Are there any questions before I jump to that part? Right. Okay. Okay, so the first key result is that this multi-fidelity linear regression estimator is unbiased. Okay. So that was our estimator. And so the first claim I'll make is that the expectation of this estimator is the expectation of xy1, which appears in the the true formulation for, or in the true formula for beta star. And that's unbiased. I'll get to that question in a second. That's unbiased for the same reason as multi-fidelity Monte Carlo. Basically, an expectation, these two terms are going to cancel because they're estimates for the same statistic, just with a different number of samples. Because our estimator beta hat MF is linear in C hat MF, then in fact, our multi-fidelity parameter estimate for beta is unbiased with respect to the true optimal parameter. It's followed from linearity. And then finally, that means our predictions are also unbiased. So that also follows from linearity of the model and the parameters. And this is significant, and it's basically saying that by introducing this low fidelity data, like we're not changing the bias of the estimator. So in that sense, the low fidelity estimator does not have a corrupting influence on the learning, even though we had even though we added this low fidelity data. Giselle, I'm going to defer that question until I talk about A, which will happen in like 2 slides. Are there any questions about this unbiased bit? Okay. All right, so the next thing I want to talk about is the error, because obviously the error of a model sort of depends not only on the bias, but also on the variance. So let's talk about what is the variance of this multi-fidelity estimator. So remember I was trying to estimate xy1, like that's kind of what cxy is trying to the mean of xy1 is what cxy is trying to estimate. So I'm going to define a function g, which is just like f multiplied by the features. So what I'm trying to do essentially is estimate, like do a multi-fidelity estimate of the mean of this function g now. And so this is the sort of high fidelity function g, and then I've got some correction terms based on the low fidelity functions g. And so I can write an expression for the variance of this estimator in terms of covariances of g. So like you see that just as a reminder, g maps to like a d-dimensional vector where d is the number of features. And so I can define these gamma 1, 1 and gamma 2, 2 and gamma 1, 2 as being the covariance of like the high fidelity with itself, covariance of the low fidelity with itself, and like cross covariance terms. Okay. And so we see that the variance of the multi-fidelity estimator definitely depends on what this matrix A is. Okay, and so that starting to answer Jill's question, makes you wonder, okay, what's the best A? So just as a reminder, when I was just estimating scalar means, like the alpha, which was a scalar coefficient, had an optimal form that was the covariance of the F1 and F2 divided by the variance of F2. And so similarly, we can show that to minimize the trace of the covariance of this, vector estimator, the optimal A star that would minimize that trace the covariance is gamma 1, 2 divided by gamma 2, like basically well, divided by, but yeah, like gamma 2, 2 inverse. So it has the same form. And so, I mean, that, kind of gives you some confidence that maybe I did my proof correctly. Um, and yeah, it does reduce to this, and like the matrix optimal thing does reduce to the scalar optimal thing. So that would be the optimal way to choose A star to minimize the variance of the estimator. All right. So we have a theorem basically saying, okay, with the gammas defined the way I've defined them, this choice is optimal in the sense that it minimizes the trace of the covariance of this multi-fidelity estimator. So it also minimizes the trace of the covariance of the parameter estimates, and it therefore minimizes the variance of the model predictions, like, conditioned on the input. So practical considerations. So I mentioned that for, standard multi-fidelity Monte Carlo, just for scalar mean estimation, we have to estimate these second order statistics of the models to get the alpha star. And we usually do that with pilot samples, and it works reasonably well across a number of applications. But just noting that for my regression setting, this optimal A star now depends on these covariance matrices being estimated because I'm estimating a vector quantity. And in general, that's going to be a harder estimation problem than estimating sort of scalar statistics and might require a high number of pilot samples. So the theoretical optimal A star may actually be quite expensive to compute. And so since we're not sure we can get good estimates of this theoretically optimal A star, we have some practical alternatives. One is to say, okay, what if I restrict A to essentially be a scalar? So A is going to be a scalar alpha times the identity. Then the optimal scalar coefficient has a form that also may not surprise you. It has, kind of similar resemblance to the optimal A star. And so this is like in this class of A, this is the best way to choose alpha star, trace of gamma 1, 2 over trace of gamma 2, 2. Or alternatively, if you don't even want to bother estimating these traces, you could just say, okay, I'm just going to just as a heuristic use this alpha star that came from mean estimation, which, is not optimal in any sense, but what we find, works reasonably well. So this slide essentially summarizes kind of the three ways that we might choose that scaling coefficient. And now I'll ask Giselle if there's any sort of follow-up questions on A. Or anyone else, if anyone has questions. Okay, glad to hear it. Okay, so I talked about choosing A. I haven't really talked about choosing M and N, which is like how to allocate the samples among, say, maybe a fixed computational budget. And I'll just say that we haven't really done this. I'm saying like we could formulate a minimization to do this, to say like what are the M and N that are going to minimize this variance. But it would be kind of complicated and would also depend on these estimates that we think in practice might be quite hard to get. So, just practically, maybe you already have data that's just like given to you, like here's some low fidelity data, here's some high fidelity data. So like probably just want to use all of it. Or as a heuristic, use the M and N that would come from the MFMC paper. So there's, like I said, an analytical formula to tell you how many samples to distribute to each model. And so that's what I'm going to do in my numerical experiments, this kind of heuristic thing. All right. So just to summarize what we were able to get out of the theoretical analysis, so the first thing is the multi-fidelity approach is unbiased with respect to the distribution of the high-fidelity data. Okay, so the low-fidelity data do not have any kind of corrupting influence. And something I want to emphasize is that this is a kind of guarantee that's possible in this multi-fidelity control variate setting that is not possible for what I would think of as more ad hoc approaches, some of which are based on transfer learning. Like you don't have that guarantee that the low-fidelity data are not corrupting. We also show that if you have variance reduction of the CXY estimator, this is going to lead to reduced variance in the coefficient estimators and therefore reduced variance in the model predictions. And that's significant because it means that the expected square error of the learned model is going to be lower relative to the high fidelity only training process. So we have improvements in accuracy as well. So before, the last thing I have for you are some numerical results. Are there questions at this point? Okay. All right, so the first thing I have is an analytical example in one dimension because I can plot the models and kind of show you how the variance looks. So I just have a uniform random variable z. High fidelity function is an exponential function, and the low fidelity function is an exponential function that we've sort of moved around a little bit, so it's a little bit off. In this case, I pretend that the high fidelity model costs 1 and the low fidelity model is a lot cheaper, so 1,000 times cheaper, and they have quite a good correlation. This is like 97% correlated, and we're going to fit a quartic model. So yeah, here's the intercept, and then I've got, first, second, third, and fourth order features. So to ensure like fair comparisons, we will say that the cost of acquiring data points is going to be fixed. And so we compare standard high fidelity only training, so just filling up that whole budget with samples from F1, with multi-fidelity training, where I use that MFMC model, like sample allocation algorithm, to determine the number of samples. And so this table shows you like how many samples go to the high fidelity model and the low fidelity model in the multi-fidelity approach. So for a budget of 10, I use 80% of my budget on high fidelity samples and kind of the remainder among M. There's a reason that like kind of a silly reason why this doesn't all add up to 10, and that's something that I could fix, but I just haven't. But anyway, so this is the number of samples that are being used for different budgets. And so, I mean, the main idea is like you sacrifice a few high fidelity samples in order to get a lot of low fidelity samples. Okay. And so the reason I wanted to have this analytical example is to basically show you how these models vary. So the black line on this plot is the best fit quartic function to the exponential data. Or, that's taking exact expectations because we can, because it's a simple example. So that's sort of the optimum with respect to the underlying distribution. These blue lines, which are plotted with some transparency, show you different realizations of the high fidelity trained model. And this is with 100 samples, which is like a lot of samples for a one-dimensional example. And so even with like 100 samples, you see there's quite a lot of variation in the fitted quartic functions for the high fidelity only data. And then in these orange dashed lines, these are also plotted with transparency. You see a lot narrower variation, like they're much closer to that beta star. Okay, so we're like just kind of, this is the visual of showing you like how much more robust the multi-fidelity training approach is. Okay, so I mean, I will walk you through this. It's kind of a lot. Okay, so now this is kind of an exploration of the dependence of the model on the hyperparameters. So like the choice of A and the choice of N and M, which depend on those estimates of statistics. So as I mentioned before, we have 3 different ways to choose that A. Like there's the optimal matrix coefficient, there's like the optimal scalar coefficient, and then there's kind of this heuristic that comes from like what you would do if you were estimating the mean. And those 3 choices of coefficient depend on estimates of model statistics. So in the left column, what I'm showing you is, okay, I'm assuming I have the exact model statistics, right? So this is the case in which like A star is optimal. And that's what you see. The A star has the lowest variance. So this is the trace of the covariance of that, of the CXY. This is the trace of the covariance of the estimates. And this is for a fixed Z, the variance of the model predictions. And so, yeah, that optimal alpha star coefficient is like the best you can do if you truly know the model statistics. And then these 2 scalar things perform kind of similarly when you know the optimal statistics, the exact statistics. And then as I move to the right, I'm estimating these optimal statistics as well as the optimal and as well as the heuristic N&M with 100 pilot samples, which is, probably more than is realistic, but and then 10 pilot samples, so that's really quite few. And then you see, okay, like when you have just 10 pilot samples, okay, theoretically the matrix coefficient would be optimal, but in fact is suboptimal because you have poor statistics that you're basing that coefficient on. But despite the fact that there is some sensitivity to estimating the statistics, we see consistently that these multi-fidelity strategies have lower variance in the predictions than the high fidelity only of the same cost. Okay, so that was an analytical example, and now I have a PDE model problem. This is a convection diffusion reaction model in a two-dimensional domain. And it's like a one-step chemistry model. And so I have 5 input parameters, which this A is not the same as the matrix A. This is now the Arrhenius reaction A. The activation energy E, temperature of the inflow, and like initial temperature at the wall, and then phi is like a fuel oxidizer ratio. So these are 5 parameters. The output I want to predict is the maximum temperature in the chamber at steady state. And my high fidelity data then comes from like a 2D finite difference simulation where the cost is 1.9, and that's actually in seconds, so 1.9 seconds. And then I have low fidelity data that comes from a POD dime model, and that has a cost of like 6,000ths of a second. And in this case, we have a 95% correlation between the models. So this is still pretty highly correlated. Okay, so here I'm showing you that for this example, so also fitting a quartic model, but to 5 inputs, so there's like, I think like 25 features or something like that. Here, the main thing to highlight is that when I'm estimating, so like I have like a ton of samples just stored, and so if I've got high sample estimates, like the A star, the matrix optimal coefficient does do better as it should in theory. But then when I have to estimate those statistics, those covariance matrices to choose the A star, alpha star, and alpha mean, the A star is not on this plot because it's like 10 to the, I don't know, like 20. Okay, so it's just so bad that you wouldn't want to do that because you just don't have good estimates for those covariance matrices. However, the optimal matrix coefficient alpha star does do much better. And so that's kind of our general recommendation in the paper. This is probably the thing to go with in practical settings. And again, like, consistently we see that like when you do that, like you get a lower variance in the predictions for multi-fidelity training than with high fidelity training of the same cost. Okay. And then here, I just want to show you how that translates to improvement in the prediction error or in the generalization error. So here I've just drawn some samples from the distribution that are not seen in training, and this dotted black line is kind of the optimal prediction error, like optimal computed with a ton of samples. Basically, it's like a very high sample reference. So that's the best we could do. And then with high fidelity only, I'm showing you here's kind of the mean over a bunch of realizations of training. And then I've got like the ±1 standard deviation and shaded, and that's over just a bunch of realizations of training on like different independent training sets. And that's for high fidelity in blue, and then low fidelity in orange. So here you really see the fact that we're lowering the variance of those predictions is significantly lowering the average prediction error or average generalization error, and also narrowing like kind of how wide that range is. So it's making it robust and it's making it more accurate. It's kind of the key takeaway. And that effect is particularly pronounced in this low budget regime, right? So like when data is scarce, that's where you're really seeing like, significant gains. So that brings me kind of to the end of things. So here's a QR code for the archive paper. And to summarize, so we have a new multi-fidelity linear regression method that combines high and low fidelity data during model training. The multi-fidelity learned models are unbiased and they have lower expected square error than standard training. But we do have a lot of open questions, like, someone was, I think Giselle was asking about, like, can we handle different inputs? Not right now, but we're thinking about it. I also presented this, like, entirely for scalar predictions, like scalar outputs, and there are some interesting questions about what you would do if you are predicting vector outputs. Um, there's also questions about like how would you extend this to nonlinear regression, which we're working on and have some ideas. There's like actually many ways you could think about extending it to nonlinear regression, as well as additional analytical questions. In particular, like Multi-fidelity Monte Carlo has a lot of literature on like how to select models to guarantee that they're going to be useful, and that's kind of something we could also do here, but have not gotten around to yet. So thank you for your attention, and I'm happy to take questions.
All right. Thank you so much for the wonderful talk. We have a question. Giselle asked how the correlation between the models affect the performance. What is the minimum correlations you'd recommend between the models for usable results?
Yeah, that is a great question. And I will say we have not done that analysis for the regression setting, but a lot of that analysis has been done for just the Monte Carlo setting, which is different. Okay. And so from the Monte Carlo setting, some of the things we learned is it's not like that there's a cutoff for the correlation, but there's a cutoff for the correlation with respect to how high the cost ratio is. So when I was doing multi-fidelity Monte Carlo for like just uncertainty quantification for a telescope model, we found we like used models with correlation as low as like 38%, with significant cost reduction. It was like a 10, 10, or sorry, 10 to the six, like 6 orders of magnitude cost reduction. And then you can show that that still leads to variance reduction. So it's really like the worse the model is, the cheaper it has to be useful. But emphasizing that that's what we've been able to show both numerically and theoretically for estimating means, and that estimating parameters of linear regression does complicate things a little bit.
Well, I have a question. So in your second examples, your lower fidelity model was the PODDIN.
Mm-hmm.
And I know some other, researcher who's working on the multi-fidelity settings. They also add the cost of the training the PODDIN model. I'm guessing you haven't included that cost.
No, I haven't. Right now, I'm just saying like I'm treating those models as kind of like oracles that we have, and then the question is like, how would you use the data that arises from that? But I mean, I think it's a good question. I know that there are other people working on these sort of context-aware approaches where you're kind of like taking into account how much, yeah, like how much effort it takes to just get the low fidelity source. So those are connecting that body of literature to this is definitely an area of interest.
Thank you. Next question is by Boris. Boris, you're
Hi,
here.
Boris.
Do you wanna
Yeah,
ask
I can also ask
yourself?
you a person.
Yeah.
Okay.
Hi, Elizabeth. Maybe I think I probably missed this. You're optimally assigning these M's and N's, right?
I am heuristically assigning the M's and N's based on the optimal model management
Okay.
approach for mean estimation. I briefly touched on this, that like you could try to formulate a problem that optimally assigns the M's and N's for the linear regression thing, but it would depend on so many statistic estimates that we don't think we can get well in practical settings, that we think that a heuristic is likely to be practically useful
Okay.
or practically useful. Yeah.
Thank you. Nice talk.
All right. The next question is by Kevin. Thanks for the great talk. The PD example didn't seem to be a linear regression problem, or maybe I missed.
Yeah, I think I was not maybe as clear and explicit about that as I should have been. So we are fitting a quartic model to these 5 parameters. So like the features x of z are like, like various for, constant and first through fourth order polynomial terms of these 5 parameters that are being fit. So yeah, so the analysis applies.
Analysis still apply. Okay. All right. Next question is by Eric Chang. Earlier, I think you mentioned something about the low fidelity model being based on some transfer learning approach possibly breaking the
Yeah.
unbiased bias of the estimator. Could you expand that?
Yeah. Let me say that like I think there's a lot of interest in multi-fidelity learning approaches. And um, people, I mean, there's so many different ways you could combine high and low fidelity data. So I've seen things where it's like you have two neural networks and one trains on high fidelity data and one trains on low fidelity data, and then you add them together somehow. Or I've seen things where you like string like, 5 different neural networks together, and some of them map between the high and low fidelity data, and some of them are just for the high fidelity data, and some are just for the low fidelity data. And I've seen things where it's like one neural network or, I mean, one model, and you just train on the low fidelity data, and then you just, at the end, you throw in the high fidelity data just to kind of update things. So there's many ways you could do this. And the point I was trying to make is that we're doing it in a way that's based on the multi-fidelity control variate literature, which has a lot of theory, including this guarantee of unbiasedness. And that is something I have not seen for these other approaches that I was just describing. Like, if you just throw in the high fidelity data at the end, you don't get that kind of guarantee of unbiasedness. Like, so, I mean, that's not to say that there couldn't exist a guarantee if you were careful about it. It's just that I haven't seen that in that literature. And so this is something that I think is an advantage of this approach based on multi-fidelity control variates.
All right, thank you. Next question is by Zachary. He asked, can you use more than one low fidelity model?
Yes. So this extends very easily to more than one low fidelity model, and you end up adding like more terms of the same kind, like more like, so you'd have like a second term with like your F3 and another term with your F4. And then in these variants that I mentioned, the generalized approximate control variates, as well as like the ML-BLUE estimators, there are like sort of even more general ways of combining those models. And I will say they're more general, and they get greater variance reduction under the assumption that you kind of have those exact statistics. So it's kind of unclear in practice, like how well you do if you don't have great statistics estimates, but there's lots of ways to add other models in.
Awesome. Well, let me ask this question. So you like the unbiased model,
Mm-hmm.
I can see.
Yeah.
In some sense, that's it can be also viewed as a modeling bias, right? I mean, you have a mean and bias, and to make it unbiased, you go another level, and then for you apply the multi-covariate method on that. So I see that like hierarchical, modeling approach. You start with the mean and second order statistics, third order, fourth order statistics, and so on and on to make the bias model to unbiased. If maybe you have a different view on that.
Yeah, that's not how I would describe it. Like I would say, this approach is really about reducing the variance of estimators of the learned model parameters. And we have an approach where we use an unbiased estimator for the model parameters so that when we combine them in the multi-fidelity sense, the multi-fidelity estimator also remains unbiased. If and we're not really using like the only higher order statistics that kind of enter into the model are the second order statistics, which are just used for choosing hyperparameters of the method. There's like no third order or fourth order statistics in this method.
Yeah, if you don't use the estimates, but at the end, in practical sense, you're using estimates.
Yeah, in the practical sense, we are using estimates of the second order statistics, but third order and fourth order statistics don't enter anywhere.
Yeah.
Yeah.
So if I rephrase my question, since you are using the estimates, there will be another bias terms which we ignore
So
due to
since
that
we're
estimate.
using the estimates, the guarantees of the optimality of the variance reduction are, sort of approximate guarantees. But in fact, the unbiasedness does not depend on those things. So no matter what, like the unbiasedness is there, even if we estimate statistics.
Okay.
Yeah, and that's just from the form of the estimator.
Okay. Thank you, Elizabeth. Is there any other question? Wow, it's a punctual 11 a.m. We started punctually at 10 a.m. and looks like we are ending punctually at 11 a.m.
Excellent. Gold star.
Gold star, yes. All right, if there has no further questions, let's thank our speaker, Elizabeth, for the wonderful talk. Elizabeth, you're the great teacher. I can see like students will love to take your classes.
I appreciate that. I hope they do. Thank you for having me.
All right, thank you. Thank you, Elizabeth. All right, that ends our seminar today. Let me stop the record button.
Well, I